Good evening and welcome to Chabot Space and Science Center's Asteroid Day Celebration. Asteroid Day is a global initiative to highlight asteroid detection, research, and the current and future missions to study them. My name is Lisa Hoover and I'll be your host this evening. Our program will feature Chabot's Galaxy Explorer interns, represented tonight by Helena Lowe, with an interview with astronaut Dr. Edward Liu on the B612 Foundation mission to protect Earth from potential asteroid risks. Our guest speakers tonight will be Dr. Thomas Prettyman, senior scientist at the Planetary Institute, and our very own Gerald McKeegan, Chabot astronomer and board member. Welcome all. We're so pleased that you can join us this evening. Let us know where you are watching from in the chat from around the globe. If at any time you'd like to make a donation to further our work of STEM education, you may do so via the Facebook donation button below or anytime via our website. Don't leave because we'll be taking your questions for Dr. Prettyman and Gerald McKeegan live at the end of our program. And if you happen to have any 3D glasses handy, you'll want to grab them for Dr. Prettyman's segment. Up first, tonight is our Teen Galaxy Explorer interview with astronaut Edward Liu, and Helena is going to introduce him. Take it away, Helena.
Thanks. Ed Liu is an explorer whose quest is to map the unknown, whether by surveying the oceans at Liquid Robotics, leading Google Advanced Projects team to map our neighborhoods, or his current work unveiling the secrets of the inner solar system. Ed co-founded the B612 with Apollo 9 astronaut Rusty Schweickart, Clark Chapman, and others. Ed currently serves as executive director of the Asteroid Institute. And as a NASA astronaut, Ed has flown 3 missions, logging 206 days in space to construct and live aboard the International Space Station. A graduate of Cornell, Ed earned a PhD from Stanford and has numerous commendations, including NASA's highest honor, the Distinguished Service Medal.
Thank you so much, and take it away, Richard.
Hi everyone, my name is Maxwell Edmund Strati and I'm this year's Chabot student-led astronomy team captain. Today, the rest leadership for the team and I are going to be interviewing Ed Liu in celebration of Asteroid Awareness Day. So I'll go ahead and turn it over to Ed. He's a former astronaut, former Google Programs lead, and the co-founder and current director of the B612 Foundation. So Ed, would you like to say a few words?
Well, no, just thank you very much for having me here. I'm happy to answer whatever you guys want to talk about.
Awesome, cool. All right, so to start off, I mean, just because today is the day, so tell us about Asteroid Awareness Day. What is it? What's cool about it?
Well, asteroids are the thing that's actually cool, and they're really important because most of the objects in our solar system are asteroids. Far and away the majority of them. You know, we have 8 or 9 planets, depending upon who you ask, but we have millions of asteroids. And the interesting thing about them is that they, you know, you can sort of think of it, if you think of the solar system as like you know, an ocean. You know, what we've got mapped right now, the things that we know about are where the continents are, so the planets. What we haven't yet mapped out is the locations and trajectories of almost all of the asteroids. Only a small fraction of them have we actually tracked thus far. And unfortunately, sometimes those things hit the Earth. So that's the bad part. The good part about them is that there's resources there. If we travel around the solar system, that's the place we'll get them from. We can talk about why that is. But they're also the orbits that they're in, the distribution of orbits in them actually tells you about how the solar system was formed and evolved, how Earth came about. And so there's a lot of information, there's a lot of great science you can do there too. So all of that is why asteroids are interesting. And Asteroid Day itself is just a sort of day of celebration of the people who work on all of these problems.
Awesome. So asteroids can tell us a little bit about the universe as such, but like what are asteroids actually made of, and I mean, how are they actually formed themselves?
Well, asteroids are really remnants of a planet that never really formed. So the majority of them are located between the orbits of Mars and Jupiter, and most of them are just rock, but most of them are I mean, but if you think about what the planets are made of, at least the planets in the inner part of the solar system, like Earth, it's mostly rock, but it's also got metals in it, right? So there's, in fact, the core of the Earth is iron, primarily iron. And what you find out there in the asteroids is that most of them are rock, but some of them have large amounts of iron because they were part of a planet, again, that probably broke up early on in the early part of the formation of the solar system. So they have a lot of interesting things in them: water, organic materials, and so on. So, but you can think of them basically as different types of rocks.
Very nice, thank you.
Ed, going off of that, I know an area of confusion is the difference between a meteor and an asteroid. Could you explain?
Well, meteors came about before people knew what asteroids even were. So the name, the word meteor, came about because it was something that people saw shooting across the sky. It's a shooting star, right? It wasn't until much later that people realized that there were other objects going around the solar system. They discovered what asteroids were, and that sometimes those things landed on Earth and were rocks that you could pick up. So there was things called meteorites, which were rocks that people picked up on the ground that they seemed to drop from when people would see these shooting stars. In fact, they are. No one realized that those were actually asteroids until later.
And also you mentioned a bit about asteroid orbits. Could you tell us about if there's anything unusual about the orbits or what we can learn from them?
Well, the orbits, first off, orbits in general, everything in the solar system orbits around the sun, unless you are the sun, right? Everything except the sun. But these orbits are there's actually a mathematical description of them, first basically understood by a guy named Kepler hundreds of years ago. And then later Isaac Newton helped understand that, and was later refined by Albert Einstein himself. But these orbits are, you can think of them as fairly circular in most cases, but sort of sometimes more ellipsoidal. But like the Earth goes around the sun, and it doesn't keep exactly the same distance from the sun. So our planet moves in and outwards a little bit, as do all the other planets. And these asteroids, most of the time, spend most of their time between Mars and Jupiter.
Okay, so given Kepler's laws and these asteroid orbits, do asteroids ever crash into each other in space? And is there any interesting phenomena that happens when there's a collision?
Yeah, asteroids do crash into each other. In fact, if you look at some of the pictures taken by some of our space probes that have gone to asteroids, you see craters on them. That's where smaller asteroids have hit bigger asteroids, right? But most empty space is mostly empty space. So most of the time, these things can go for millions of years without hitting anything else. Okay, but sometimes, however, if you look at their orbits, some of those orbits actually cross the orbit of Earth. And you can think of this as two different cars, both going around two racetracks, both around the sun. But the racetracks are different. Those are the two orbits, which are different. But there's an intersection. Okay, and most of the time that's fine. If you think of, I don't know, has anybody here ever seen a demolition derby? Know what that is? Okay, this is something that was probably popular back in the 60s and 70s. People used to take these junker cars, and they would take them to some like a showground, like the old State Fair in New York had this. And people would buy a car for like a couple of $100, barely able to move, and they would drive around these rings and sometimes run into each other, and the last car that doesn't break down is the winner. It's called the demolition derby. Rather silly, but in any case, the asteroids kind of play this big game of demolition derby going around the sun. They have their own, each of them has their own individual racetrack. That's their orbit, including the planets. But sometimes those orbits are actually intersect each other. But mostly there isn't a collision as long as the two objects are not in the intersection at the same time, right? So picture two race tracks with cars going around them. However, if you get two cars in the intersection at the same time, then they can hit, right? So it's a really matter of timing. And what we know is that there are hundreds and hundreds of asteroids, maybe and thousands in fact, whose orbits actually cross the Earth. So those are the ones that someday will hit the Earth. And the question is when? So you have to be able to understand the timing of these things in order to calculate when some of those might hit the Earth.
Hey, thank you. That's definitely very interesting. So what causes asteroids to escape the asteroid belt and drift off course?
Yeah, well, these things are mostly minding their own business, going around their little racetrack, right? But then sometimes a planet comes near them, or they come close to a planet. So maybe the racetrack of Jupiter happens to be near their orbit. And at some point, Jupiter came close enough to these things that the gravitational pull of them changed their orbits. And that's the primary means by which asteroids change trajectory. They come near a planet. Jupiter, being the biggest planet, affects their orbits more than the other planets. But basically, when you get close to a planet, their gravity gets a whole lot stronger, and it can pull you in a different orbit. And over millions of years, that begins to throw asteroids out of this asteroid belt into orbits that go towards other parts of the solar system, like Earth's orbit. Those are the ones we have to worry about, because if those are actually the ones that are most interesting, because if they come close to Earth, that actually makes it easy to send a space mission there. However, if you come close to Earth, sometimes they can run into Earth. So they're both good and bad. When they come close to Earth, also, it's much easier to get our telescopes on them. So it's great for doing science, great for doing missions, bad from the standpoint of they might hit the Earth. So it's a double-edged sword.
All right, so we just went over a lot of basic asteroid content, but fundamentally, kind of as a takeaway, what is probably the most important thing that we could learn from asteroids?
I would say that it depends on who you ask. I mean, I think they're fascinating for all these different reasons, right? If you're a scientist and you want to study, how the solar system works, well, a great place to start there. If you are thinking of flying missions into space or want to be involved in the future of space development, that's a great place to visit. The bodies that come closest to the Earth, easiest to reach. If you want to protect the Earth, well, they're important too. So it just depends on who you ask, I think.
All right, and before wrapping up the general asteroid questions, before we talk about the B612 Foundation, do you have a favorite asteroid?
Good question. I guess I'd have to say I actually got lucky enough, and I have one named after me. So myself and another astronaut, a guy named Rusty Schweikart, were both the Jet Propulsion Lab, NASA's Jet Propulsion Lab, named an asteroid after each of us. And so we were at a scientific meeting together. This was probably about 15 years ago or so, something like that. Rusty and I were there, and the leader of the JPL came up and said, "Congratulations, we've named an asteroid after each of you." And so, of course, Rusty turns to me, and I turn to him, and we both say, "So which one of ours is bigger?"
Wait, can I get an asteroid named after me too? Is that possible? No.
Maybe someday. Well, yeah. I mean, asteroids have been named after lots of people, and there are lots of asteroids. So I think you got a good shot.
Alrighty, nice. And so you're the co-founder and director of the B612 Foundation. And so we wanted to ask you today, can you tell us a little bit about what your foundation does? What's your guys' mission? What are you guys all about?
Yeah, we're trying to protect the Earth from those big asteroid impacts. Now, remember that small asteroids hit the Earth all the time. Those are the shooting stars you see. Those are things that provide the little meteorites you pick up on the ground. And those are not a problem. It's those big ones that occasionally hit the Earth that are the real problem. For instance, the history of life on Earth has actually been punctuated numerous times by large asteroids that have nearly wiped everything out. An example of which is the one that killed off the dinosaurs, but it's just one of many mass extinctions on Earth that have been caused. Probably 100 mass extinctions on Earth have been caused by asteroid impact. So they do happen. And it would be a shame if it happened on our watch in some sense, right? Because now what's different is we have the space technology to see them coming. We have the mathematics and physics to understand, to predict, hey, that asteroid that we see there, that's going to hit us in 35 years or whatever. And we have rockets and space technology that allows us to gently nudge these things to keep them from hitting the Earth. So at this point now, we've just got to the point where we as human beings can actually protect the Earth. And so that's what we're trying to do.
Nice. And so like protecting the Earth is like obviously important, but like also like what really inspired you to pursue this work? Like what got you interested in trying to create an organization like B612?
Well, it was really that. It was that realization that, you know, let's say a large asteroid had been headed towards Earth 100 years ago and wiped all of humanity out. That would have been bad luck, right? That's the definition of bad luck. There was nothing anybody could have done, right? If it happens in 20 years or 50 years, that's not bad luck anymore, because now we can do something about it. You know, that's, I would say, negligence on our part, right? So, you know, that was really our goal in starting this organization, just to help put together the various pieces that allow us to protect the planet like this.
This like obligation you feel as to like do this type of work because now it's actually possible to. Okay, that's nice. That's nice.
Exactly,
And
I think it's also part of developing space. Something I think is important too. You know, the human beings moving outwards into our solar system is, I think, something that is inevitable, and so I feel really important about that. And I love the science too. So when you throw it all together, it seemed like a good thing to work on.
All right, yeah, that's great. That's cool. And so why the name B612? Just cool thought, any personal significance or like
Yeah, a long time. Anybody here ever read the book The Little Prince? Probably a lot of people have read it. You may recall that the Little Prince in that book was from an asteroid called B612. That's where we got the name.
That's amazing.
Cool.
That book was my childhood.
Yeah, it's a fun book, isn't it? I mean, our daughter loves it too now, and there's a little something in it for everyone. And the basic moral of the story is that sometimes adults fail to see what's important, right? And the Little Prince makes it a point that it is important to look up on occasion, and you know, that's the whole idea. Sometimes the adults are too busy thinking about which actor insulted which other actor, or which politician insulted which other politician, or something like that, and they fail to look up and see the big picture.
And that's actually like really powerful. That's really cool.
Yeah, I agree. I mean, and you guys are the future of this, right? Because this is something that is going to take us, you know, years to develop all these things. You know, we're coming along right now. Where the first test of an actual real asteroid deflection is happening next year. It's a test being run by NASA and the Applied Physics Laboratory. They're going to deflect a small asteroid on purpose and measure how far it deflects it. We are also, the big problem is actually finding and tracking all these asteroids first. You need to know which one would be a threat and be able to calculate, you know, when any particular asteroid might hit the Earth. And we can do that down to the microsecond. So that's actually what we're working on is the warning systems, and that's most of the battle, as it turns out. And so we're working with some of the large observatories, and so these things are going to be going on for years. So we're just at the beginning stages of this.
Well, thank you, Ed, for your time. And just wrapping up this interview, we just want to ask one more thing. So as a takeaway, how can non-scientists get involved in asteroid research?
Well, I check out the website for Asteroid Day. There are a lot of there are citizen science opportunities that are out there. I know that. And I think just telling people, you know, I love to tell people about science and asteroids, and you know, you guys are going to be the ambassadors for that. And I think that's really important.
Cool, great. Well, thank you for your time. This has been definitely really awesome. You've been a huge inspiration. Thank you so much for like taking time out of your day to speak to all of us here at Chabot. We're all really thankful for it. And for those viewing at home, I'm sure they're very appreciative of this too. So, you know, feel free to just when we reopen, come by again. We'd love to have you.
Yeah.
See you speak
Well,
again. Great.
Thank you to all of you. Great questions, by the way. And I'm really happy to get to talk to you, and maybe someday at some time we'll get a chance to meet in person. So thanks again.
Hi everyone.
Great. Let's see some appreciation in the chats for Ed Lu and his gracious time that he's given the Galaxy Explorers and for their interview and questions. I thought that was fantastic. We have another Galaxy Explorer joining us this evening. Banu Afkami, I got your last name correct, and she is going to introduce our next guest speaker. Before she does, if you missed any of our program and are just watching us late, you'll be able to watch it in its entirety on YouTube later or for repeat on Facebook. And we see your questions in the chat, and we're going to get to those right after the speakers, so keep them coming, stay tuned. We're going to answer them now. Banu, over to you.
Right, so let's give a warm welcome to Dr. Thomas Prettyman, who is a senior scientist at the Planetary Science Institute. He has worked on several NASA missions, including Lunar Prospector, 2001 Mars Odyssey, and Dawn. He was the principal investigator for the gamma ray and neutron detector investigation on Dawn, which explored the two most massive bodies in the main asteroid belt, 4 Vesta and 1 Ceres. He is co-investigator of the Psyche mission to the main asteroid 16 Psyche and the Luna map CubeSat mission to the moon. His research is focused on what asteroids can tell us about the formation and evolution of planets in our solar system. So please, let's all give a warm welcome to Dr. Thomas Prettyman.
Thank you so very much for the introduction. And I'm going to share my screen. I'm going to be giving a talk. Let me make sure I've got it shared first. And let me confirm with the host that you can see my chart. Is that correct?
Yes, we can see it.
Yes.
And can you hear me okay?
Sounding good.
Okay, so I'm going to talk a little bit about exploring the main asteroid belt from the perspective of science. And this is work that I've done on the NASA Dawn mission, but also the upcoming Psyche mission that was just discussed. And so I'll start out covering a little bit about the connection between meteorites and asteroids and their origins and what they mean to solar system evolution. And I would say that meteorites have been known about for a long time. You actually find meteorite metal in Bronze Age artifacts. And the pictures that you see in this chart just show falls in Seesheim and Chelyabinsk. So in Seesheim is back in 1492, and Chelyabinsk is in our recent memory. So we have these objects that we can pick up, we can take into the laboratory, we can pick them apart and really do detailed chemical analyses. We understand that most meteorites are chips off of asteroids. And because we can do these very, very, very detailed analyses, we can learn quite a lot about our beginnings, how the solar system began and how planets formed and evolved. So just a little bit about the origin of asteroids. Asteroids originated nearly 4.6 billion years ago at the beginning of the solar system, and they represent the building blocks of planets. And so in the beginning of the solar system, there was a giant molecular cloud, and that cloud condensed to form a star, our sun. And around the sun, there was a accretion disk that formed, and bits of dust aggregated together. And there was an oligarchic growth that led to the formation of small bodies. These small bodies coalesce together to form larger bodies and then ultimately planets. What people typically don't know is that meteorites tell us about this chronology pretty much everything we know about the early solar system timeframes are derived from these objects. And it all took place rather quickly. The Earth-Moon system would have formed within the first few tens of millions of years. So in that context, the importance of meteorites to society, which is good to remember on Asteroid Day, is they tell us a bit about science. They're important in terms of planetary defense, and they might be a resource for us in the future. So what about their discovery? So on the right is a plan view of the solar system. I've marked the distances in astronomical units, and I'm looking at the inner solar system. So from Mercury to Jupiter, and you can see the scale ranges out to about 6 astronomical units, and astronomical unit, or AU, is about 93 million miles. And for a planetary science, somebody who works with robots, the fact that it takes light 8 minutes to traverse 1 astronomical unit, which is about the mean distance from the Earth to the Sun, is really important, because if you want to command a rover or a robotic spacecraft, you need to account for the fact that it's going to take quite some time to reach the spacecraft, and then it's going to take time to find out whether or not the spacecraft did what you wanted it to do. So I like adding light minutes to the scale in addition to astronomical units. But there is a solar system. This was certainly known to the ancients. The position of the planets were charted by Tycho Brahe in the 1570s, and then Kepler came along and actually determined their orbits. And you'll notice that there's a large gap between Mars and Jupiter, and that certainly drew Kepler's attention, and it was enticing because planets were being discovered, and the question he had was, could there be a missing planet there to fill in that gap? And sure enough, in 1801, an Italian, Giuseppe Piazzi, discovered one Ceres in Sicily. The telescope he used is depicted, and you can see Ceres' orbit. It fills the gap between Mars and Jupiter. And so for a while, Ceres was the 5th planet. Ceres, by the way, is the root of cereal, and it's the Roman goddess of agriculture, essentially. However, not long after that, Vesta was discovered in 1807 by a team led by Olbers, and the famous mathematician Gauss calculated the orbit of Vesta and suggested that it be named Vesta, the Roman goddess of hearth and home. These are the 2 largest bodies in the main asteroid belt. Today, we know that there are hundreds of thousands of small bodies in the orbit between Jupiter and Mars. And I've provided an animation of these. And these are mostly broken up bits of planetary embryos. So there was a collisional environment in the early solar system. The region is mass depleted. So Jupiter is sort of the big bully of the neighborhood. You can get into resonances with Jupiter and get scattered out of that region. And so what's left there, a planet didn't form, so what's left there are remnants of these embryos that built planets. And so if you were to go there and look at these, you'd be looking at some of the most primitive objects in the solar system. They have a wide range of compositions. They can be rocky, they can be icy, and on the Dawn mission, we had the opportunity to look at one rocky body and one icy body, the 2 largest ones. So there they are, Ceres and Vesta, and I provided some context for you. So both Ceres and Vesta, their profiles are overlain on top of the state of New Mexico, one of my favorite states. And you can see they're comparable in size. You might wonder how much mass is in the main belt. Well, it's not much. If you add it all together, all the bits and pieces together, it wouldn't add up to the mass of the moon. So it really is a small amount of material, but hundreds of thousands to millions of objects are there. And smaller bodies are shown below. They can be compared to features that you can think about, like a soccer field or the Albuquerque metropolitan area. But these tend to be small bodies. You'll notice that Ceres is round. That means that it's probably largely intact since the beginning of the solar system. Vesta is nearly round, but it's been battered by collisions. We'll talk about that in just a second. But because they are largely intact, they are thought to be examples of planetesimals or planetary embryos. So returning to the asteroid-meteorite connection, I have on the right a profile of what we think Vesta's interior might look like. Turns out Vesta would have melted due to the presence of short-lived radionuclides injected into the solar system by a nearby supernova, and it would have melted. That radioactivity would have decayed away, followed by cooling. You would have iron-rich particles settling to form a core, and you'd have a mantle and a crust. All of this is kind of a magmatic system, very similar to the Earth, and as a result, we like to think of Vesta as the smallest terrestrial planet. So it turns out that there are meteorites that we believe come from Vesta, and Vesta is the only asteroid that has a meteorite connection, and there are at least 1,000 of them. And these are basalts. They're thin sections that are shown above the pie chart. And there are also examples of what must be on the surface of Vesta as well. So we know that, or we believe we know that Vesta is connected to the HEDs just by looking at the spectrum of light that's reflected off Vesta and comparing it to that of these meteorites. And this was a correspondence that was established in the 70s by Tom McCord. And you can see a rather nice comparison between Vesta and the HED meteorites in the chart. So how did these meteorites get to Earth? Well, remember, Vesta's not round. There was probably a large impact that didn't quite obliterate Vesta, but sent debris off into space. And that debris was further chipped away by impacts. And then some of it got into locations where they could be easily scattered in towards Earth due to gravitational forcing by Jupiter. And so we wanted to learn more about this with the Dawn mission. Ceres was an enigma. We have no meteorites from Ceres, and we had the opportunity to test the connection between Vesta and the HED meteorites, and that is the basis for the Dawn mission. So we're looking at Vesta, which we know is igneous, magmatic, volcanic, if you will. And we're looking at Ceres, which is known to be water rich. For Dawn, launch was back in 2011. Oh, I got that wrong. 2007. So sorry, Dawn fans. But it was 27 September. And we did a gravity assist at Mars. We went through cruise, and then we encountered Vesta, went into orbit around Vesta, and got as close as about one body radius altitude away. And then we left Vesta and went to Ceres and orbited that. The entire mission was about 11 years in space. And during that time, we got very, very detailed pictures of the two largest bodies in the main belt. Just a little bit about the spacecraft and the launch vehicle. The launch was on a Delta II, and the Dawn spacecraft was propelled by ion propulsion. And so you're basically electrostatically accelerating xenon ions out the back of your spacecraft. And you can do this continuously. It's a very simple system that's reliable. And you can thrust for a long time, imparting a change in velocity and spiraling out further and further away from the sun. And it turns out that Dawn's propulsion system imparted as much delta V as the rocket that was used to launch it from Earth's gravity well. So the pictures that you see of Vesta and Ceres are from our close approach. And just for context, Hubble Space Telescope took pictures of Vesta, and you can see that Vesta is extremely blurry. In order to get detail, you really have to get up close. So I'll show you some of the details. Here's Vesta up close. On the left, if you do have 3D glasses, you can look at the 3D image, is a view of Vesta. We saw a large mountain inside of an impact basin. And when measured from the floor, this mountain may be the largest mountain in the solar system. The impact basin is called Rhea Silvia, and the mountain is about 14 miles high. And then also the edge of the basin, which is almost the diameter of Vesta, is also quite distinct. There's a lot of relief on Vesta. And if you remember back to the video I showed you of the impact, this is similar to what you might expect to see. So beautiful detailed views of this object. Here's a movie flying over one of my favorite craters. This is Marcia. It's part of the Snowman complex. It's right behind my head if you're looking at me talking. And you can see the very, very detailed views that you can get. This is obviously a simulation. We didn't actually fly the spacecraft this way, but you can see interesting features, pits in the center of the crater. But Vesta largely confirmed our expectations that we had based on telescopic observations and the HED meteorites. And we were able to do geology on a small body in the main belt for the first time. Ceres, I told you, was water rich. We'll talk about it a little bit more, about 30% water. Vesta's very dry in comparison. In comparison, Ceres is round. There's very little relief comparatively on the Ceres surface of Ceres. The highest mountain that's there is Ahuna Mons, which is about 2 miles high, and it's shown on the right. It's extruded cryomagmas that would have formed inside Ceres crust. There's evidence for cryovolcanism on Ceres' surface. One of the more notable features of Ceres are the bright spots or faculae. And these are carbonate deposits that would have erupted onto the surface from a deep brine reservoir or from brines formed by heating that formed the crater that the bright spots are found in. The crater is called Akator. And so there's evidence for hydrothermal activity on Ceres, which might mean that there's a subsurface ocean that exists today. We detected organic matter in and around one crater on the surface, and we suspect that organic matter is pervasive in the surface of Ceres. There are all kinds of really interesting flow features and features that indicate ice is present very close to the surface, and water has been detected on the surface as well. So Ceres is the water-rich end member, sort of to visualize how much water is there. Here's the USGS's accounting of Earth's water inventory. So you can see the big blue blob is all the water that would be in the Earth. And it's not a large amount. We have a lot of water on the surface. Earth, like Vesta, is an igneous body. And it's possible that the water was delivered later by asteroid impacts during a large-scale restructuring of the solar system. But the blue blob next to the label Ceres is, a depiction of how much water Ceres has. And it's interesting that even though Ceres is tiny, it's comparable to that of the Earth. So Ceres has just about everything you need if you're an astrobiologist. It's got the right chemicals, the right chemistry. There's water present as water ice on the surface, but probably is liquid in the subsurface, at least in the distant past. And there's energy. All of that links into habitability. So Ceres could have been habitable at some point. And so we're hoping that we'll go back at some point and get a sample, maybe with a sample return mission, and maybe you could be involved in that. So changing gears, we've looked at two bodies that are largely intact, but what if an object like Vesta got hit by a high velocity collision? Well, that could have stripped off the mantle and crust, revealing the core. And so that's sort of the basis for the NASA Psyche mission. One idea is that if you had a Vesta-like object that was still partially molten and it got hit by an impactor, you could strip away the outer layers. You would have a molten blob of metal in space that would gradually cool. You could form a dynamo like the Earth has, and you could have a magnetic field, and that field might be imprinted on the surface materials. And then ultimately, you would cool. So some of the really interesting things, this picture shows yellow liquid squirting out of this object, and that's one possibility is you might have had sulfur volcanism. So there are all kinds of really interesting things you might see if you were to see a stripped core in space. So why Psyche? Well, it turns out to be the 10th largest asteroid in the main belt. It's smaller than Vesta. It could be comparable to the size of Vesta's core. A lot of the data we have, including estimates of its density and reflectance spectra, suggests that it might in fact have some metal on the surface or be made of metal. And the key thing is it's accessible by a discovery mission like Psyche. So the Psyche spacecraft is in development. There's a picture of it. It's got instruments that you would need to measure the magnetic field, a magnetometer. It's got a gamma ray neutron spectrometer to measure elemental composition. And it's got an imager to take pictures and also to see what minerals are on the surface. Mission timeline, again, we're in development. We don't launch until 2022. Very, very similar profile to the Dawn mission because we are also using ion propulsion to do this mission. It's very cool. Here's kind of where we're at. There's a picture on the left of Psyche under construction at Maxar in Palo Alto. There's a tiny portion of the Dawn team is shown there. It was recently delivered to JPL. Ultimately, the instruments are going to be integrated, and we'll get the spacecraft to the launch pad. Just to drive home one of the key points, we think of these missions, these robotic missions, as having the potential to transform blurry points of light that an astronomer would see in a telescope into geologic worlds. And so here are some pictures of those blurry points of light. Here's Psyche in a telescopic image from the principal investigator's backyard. And just a few days ago, we had an image come in from Mars. This is Psyche is seen from the high resolution stereo camera on Mars Express. Kind of cool. What will Psyche look like? Who knows? There's an artist's depiction on the left. What Psyche will do for us is it explores the interior of a small body that represents the building blocks of Earth and the terrestrial planets. And what I think is really neat is that Psyche also links to Earth science and that it complements efforts to understand terrestrial cores. So all this is fun. What's in it for you? Well, you can get involved. There are some great programs for students. You can follow us on social media. We have capstone projects for seniors. There's a Psyche-inspired project to produce the artwork that's displayed in the chart. And if you go to the Get Involved link that's shown below, you'll find a lot of other ways to engage. One thing I would say is that for students who are listening to this, I was asked to let them know that there's a July 30 deadline for applications to the Psyche-inspired program. Well, that concludes my talk. And I thank you for your attention.
Thanks so much. It was really informative. I learned a lot. I'm sure that everyone watching did as well. Those of you who are asking questions, keep asking them because we're going to get to them right after our next presenter. Our next speaker is our very own Gerald McKeegan, fan favorite. He joined Chabot in the year 2000 as a volunteer and adjunct astronomer. He serves on our board of directors and is a key member of the East Bay Astronomical Society. Gerald holds a Master of Science degree in space studies and has over 40 years of experience working in the space industry, where he's been involved in numerous space projects, including the Space Shuttle, the Cassini, the Mars Reconnaissance Orbiter, Mars Insight, Solar Beam, Juno, and so much more. He's the 1988 recipient of the NASA Silver Snoopy Award, and his work has supported the Challenger Space Shuttle Return to Flight program. He also heads Chabot's Near-Earth Asteroid Research and Tracking program right here. And they have discovered more than 2,000 asteroid observations using Chabot's telescopes. Without further ado, I will turn it over to Gerald.
Well, thank you. Just wanted to clarify one thing. We did not discover 2,000 asteroids here. We don't discover asteroids here at Chabot. We just track them. So I wanted to talk a little bit about how we do that. And if you'll hang on just a second here, I'm going to share my screen. And hopefully everybody can see that. So again, we're with the Chabot Space and Science Center up in the Oakland Hills. Got an image here, I think. Hang on just a second here. Let me get this to advance correctly. There we go. All right, so this is an image of the Chabot Space and Science Center. It is located in the Oakland Hills. It's about 1,500 foot elevation. We are surrounded by parkland. Unfortunately, we are also surrounded, the parkland is also surrounded by cities. So we get pretty bad light pollution up here. But if you look at the facility here, if you look over in this part of the facility, you'll see that there is an observatory complex. And that's where our observatory is located. That's where we do all of the asteroid tracking work that I'm going to be talking about. This is a view of the observatory deck. This is a wide angle view. We have three major telescopes at Chabot. The original Oakland Observatory telescope, which was built in 1883, is this one little one over here. In the Big Dome, we have our 20-inch refracting telescope built in 1915. But the one we use to do all of the asteroid work is neither of these two. It's the one that you can barely notice over here, a little guy, which is actually our biggest telescope. It's in a different type of building. It's a rollback roof observatory rather than a dome. But this is the telescope that we use to do our asteroid program. We give that telescope a name. It's called Nellie, and it's a 36-inch reflecting telescope. So our focus is not on asteroids, looking for asteroids out in the main asteroid belt. So unlike Tom, who's primarily focused on the main asteroid belt, we are primarily focused on near-Earth asteroids. These are asteroids that come close to or cross the orbit of the Earth. And right now we know of about 27,000 of those asteroids, and we think there's probably 1 million of them out there. So how is it that we go about finding them? Well, as I said before, Chabot Space and Science Center is not in the business of discovering them. Our telescope is not the right kind of telescope for discovering near-Earth asteroids. That work is done by several what we call survey telescopes. There are several of them around the world, a couple, or actually 3 of them in Arizona, up on the region of Mount Lemmon, near Tucson. Pan-STARRS, there's now actually 2 Pan-STARRS, Pan-STARRS 1 and Pan-STARRS 2 on Haleakala in Hawaii. And there are a couple other survey telescopes as well. And the thing that a survey telescope does is it has a very wide field of view. And so over the course of the night, it can survey a very large part of the sky. And by doing that, what they're looking for is a star that appears to be moving. And you'll see this in a few minutes here, but the word asteroid actually means star-like. And you'll see in a few minutes, it looks just like a star, except it moves relative to the background stars. So these are the survey telescopes. They're the ones who make most of the discoveries, but supplementing them are roughly 300 observatories around the globe that have a much smaller field of view, but they sort of zero in on the potential discoveries made by the survey telescopes. The typical scenario is a survey telescope sees a possible new asteroid. That data is sent to the International Astronomical Union's Minor Planet Center, which is in Massachusetts. And the Minor Planet Center is sort of the clearinghouse for all of the asteroid observations from all over the world. And they will then make a preliminary calculation of the orbit and post basically a request on their website for additional observations. That's where we come in. We will then go and attempt to confirm that there's an asteroid out there where the survey telescopes made their observations. All of these observatories around the world, there's about 300 or so, they all submit their data to the Minor Planet Center. And the Minor Planet Center does all the calculation work, and they share their data with NASA JPL, and it's part of the planetary defense effort that's coordinated by NASA headquarters in Washington, D.C. So just referring to what we do at Chabot, you can see here up in the left, you can see that Chabot Space and Science Center is one of those 300 observatories. And what we do at Chabot is kind of focused on 2 things. First of all, confirmation. As I just mentioned, if a survey telescope spots an asteroid, they will send that data to the Minor Planet Center, which then puts that onto a list called the Near Earth Object Confirmation Page, and we will go to that confirmation page and pick any of the asteroids that are within the range of our telescope, and we will attempt to confirm these new discoveries of near-Earth asteroids. We also do a lot of what's called follow-up. Follow-up is where an asteroid has already been cataloged, or it's already been observed enough times to where we're sure that it actually is out there. And we just continue to do observations, because the more observations you have over a period of time, the better your ability to calculate a very accurate orbit. And of course, that's one of the critical things we need is a good orbit prediction. So that's what we're trying to do. When we do our observations, there's basically 2 groups of information that we look for. One is what's called astrometry. This is where we look for the position of an asteroid in a field of view. So we will try to determine the asteroid's position in the sky using a coordinate system that is very familiar to astronomers. And it's similar to the coordinate system that we use with our GPS satellites and so forth. Right ascension is motion or the position. East and west, declination is the position. North and south. And so we get this position information, but we also need very accurate timing. And we actually run some software on our computer that keeps the computer clock very accurate. Because these observations are useless unless you know the exact time of those observations. The other data that we look for is called photometry, and this is basically measuring how bright the asteroid is, what its luminosity is. We normally do that at a specific color wavelength, and that data is then used to estimate the size of a near-Earth asteroid. So what I'd like to do is just kind of show you the process and give you an idea of how it works and let you do a little asteroid hunting while we're at it here. So the first thing we do is we point the telescope at some part of the sky where we think there's an asteroid, and we take 3 or 4 images over a period of time. It can be anywhere from 5 minutes apart to half an hour or more between these images. And if we're lucky, we find an asteroid in these images. Now, for those of you who are really sharp-eyed, you look at these 4 images and you probably have already discovered where the asteroid is. But for most of us, it's not quite so easy. So we have to do a little bit of processing of these images. So we've got, in this case, 4 images, all taken of the same part of the sky. And what we do is start to process them. The first thing we do is we match the stars in the images to a reliable catalog of star positions and star brightnesses. And there are several of those out there. We use Gaia 2, Gaia Release 2, which is a recent star catalog produced by the Gaia spacecraft. Very accurate positions and brightness data and so forth for literally billions of stars. In the past, we've used UCAC 4, and if you really go farther back, we've used other catalogs as well. So what we do is we look at an image. We know where the telescope was pointed when we took that image. We know what the scaling of the image as far as how much of the sky we can see with a given telescope. And we feed all that data to the software. The software then queries the database and matches stars in the image to the stars in the database. Once you do that, you can then scale that image using that coordinate system that I mentioned, the right ascension and declination. You can match pixel positions in the images to the coordinate system, right ascension and declination. And that's critical for us to then determine what the position of the asteroid is in each image. So once we do that, we then take the images and we do what's called blinking, which is just making like a little movie. And sure enough, there's the asteroid, and we usually can see it pretty well. And if we can't see the asteroid, we always just look for the blue arrow and it tells us where it is. So once we've got, we know we have an asteroid in our images, we need to get some data. So we go back to our individual images, and there are the asteroid positions in each of these 4 images. And then we get some data. And we use specialized software to do this. It gives us a good indication of the quality of the image, what the signal and noise ratio is, and so forth. And it tells us the position. Once again, we've created an equation in the software to relate the pixel position in each image to the right ascension and declination coordinate system. And the software then makes a calculation of what the position is in each individual image. It also tells us the exact time of the image. If the image is a, say, 30-second or a 1-minute exposure or something like that, this will be the time at the middle of the exposure. And it also gives us an estimate of the brightness in a particular wavelength. In this case, we're using the red wavelength. And that's the data that we need to submit to the Minor Planet Center. We submit that data using email. Currently, that's the method we use. We'll send an email to the Minor Planet Center. That email has to be formatted in a certain way. It has to be a text-only email. We can't use HTML. Text only, and the formatting is prescribed by the Minor Planet Center. And the reason we do that is because it's not read by a human being, at least not initially. The email is read by a computer, which then matches our data with data from other observatories and uses that, crunches the numbers and uses that to determine the orbit of this asteroid that we're looking at. Quite often there are multiple observatories around the world looking at the same asteroid. And so the computers at the Minor Planet Center, they just combine all that data and they come up with an initial estimate of the orbit, and eventually they get enough data to where they can say, okay, this asteroid is real. It's not one we've cataloged before. And we've got enough data now to publish an orbit for it. And so then they issue what's called a Minor Planet Electronic Circular, or MPEC. And that's the document that actually gives the asteroid its official designation. The designation that they use is the year of discovery, a letter code that tells you the half month of the discovery, and then another letter and some numbers that give you the sequence of discovery. And once they've done that, the asteroid is officially cataloged, and then you want to go back and do more observation to do lots of follow-up work to better calculate the orbit. And of course, the thing we all want to know is there a possibility that asteroid is going to hit the Earth? So that's the process we use. When all this is done, the asteroid gets cataloged, and there is an organization at the Jet Propulsion Lab in Pasadena called the Center for Near-Earth Object Studies. And they actually have a website where you can go and look to see if there are any asteroids coming close to the Earth anytime soon. And there are always asteroids passing by the Earth. Most of them pass very safely by the Earth, and they're not an issue. There is a small subset of asteroids we call potentially hazardous asteroids. Those are asteroids that are larger than 140 meters and come within 0.05 astronomical units of the Earth, which is a little over 4 million miles. And those are considered the ones that have the potential to do damage on the Earth should they eventually come around and hit the Earth. Now, there's an interesting thing that I wanted to just show you a little bit about here. If you imagine the Earth out there orbiting around the sun, and then there's the moon orbiting around the Earth, this diagram does not show this to scale. The moon is actually much farther away from the Earth than shown in this diagram, but we had to get everything onto one image, so I've kind of compressed it a little bit. But if you take the distance between the Earth and the moon, we call that one lunar distance. So that's this distance here, and it's about 384,000 kilometers, or about 239,000 miles. And then if you imagine a sphere around the Earth that has a radius of 384,000 kilometers, that sphere basically has a radius of one lunar distance. And the thing is that if an asteroid comes through that sphere, it's really easy, or usually pretty easy to spot. And so it's a good way of kind of coming up with an estimate of the total number of near-Earth asteroids out there. But it also gives you a little bit of a scare if you think about what's going on in that sphere. So if you imagine an asteroid passing through that sphere, we most of the time detect them. And we have some statistics on that I wanted to share with you. And this is going back to the year 2020. And I just wanted to share with you how often an asteroid passes through that sphere, how often an asteroid comes closer to the Earth than the moon. In the year 2020, 106 asteroids passed the Earth at a distance less than the distance between the Earth and the moon. Of those asteroids, the largest was 146 meters. Most of those asteroids are much smaller, but there was one that was 146 meters. The asteroid that came closest out of that 106 asteroids, the one that came closest to the Earth was about 6,754 kilometers away from the Earth. But that is the distance between the center of the Earth and the center of the asteroid. When we do the calculations for coming up with these distances, we treat the Earth as a point source rather than a big ball. We treat it as a point source with all of its mass at the center. So when we give these distances, it's the distance between the center of the Earth and the center of the asteroid, 6,754 kilometers, which means the asteroid was actually about 383 kilometers above the surface of the Earth. That's in the region where satellites, low Earth orbit satellites, the space station and Hubble Space Telescope, that's about the distance that they are from the Earth. So that was a pretty close approach. Of the 106 asteroids, 100 of them were smaller than 30 meters. And that's good news because we are fairly certain that asteroids smaller than 30 meters are going to break up and burn up in the atmosphere. They're not going to make it all the way down to the Earth, so we don't have to worry about them forming a crater on the Earth or anything like that. So most of them, 94% of them were 30 meters or less. And we've done this study now for several years, and it's been pretty consistent. Most of the near-Earth asteroids are actually pretty small, the size of a car or a bus or something like that. They're not big, huge things. But occasionally we get a big one like that 146 meter asteroid. That asteroid, had it hit the Earth in a populated region, that would be an asteroid big enough to do a lot of damage. It could wipe out a city. If it landed in the middle of San Francisco, it would have wiped out the city of San Francisco. Fortunately, it passed safely by, which is true for almost all of these asteroids. A while ago, Ed Lu was talking about deflecting asteroids and how we need to know well in advance that an asteroid is likely going to hit an Earth. So obviously it's really important for us to discover these asteroids and find them months, years in advance of their closest approach or their impact. But there's another statistic I want to throw at you here that kind of might be a little discouraging when you think about that. Of these 106 asteroids that pass the Earth closer than the moon, or at distances less than the distance to the moon, 51 of them were discovered after closest approach. So we still have a long way to go before we reach the point where we can find threatening asteroids far enough in advance to where we can actually go out and deflect them and prevent them from hitting the Earth. Fortunately, as Ed alluded to, there are some efforts being done in that direction. The DART mission that he mentioned that will launch later on this year and next year will actually deflect a small asteroid. That's a test of that technology. And NASA just approved a new spacecraft called NEO surveyor mission. And that mission will actually be a space telescope mission that will actually survey for asteroids out in space. Has a much better chance of finding all these asteroids long before they are a threat to the Earth. All right, so that's my presentation. I guess we can open it up, Lisa, now to questions. All right.
All right, some of our explorers here are going to help us with some of these questions. Go ahead, Jean.
All right, so starting from the top, someone was wondering if it's possible to capture an entire asteroid and bring it down to Earth.
Let's hope that doesn't happen. So the question is a great one. It's I think it taps into the resource idea that if you could go to an asteroid, could you move the material? Let's say it was metal or something that we use on Earth and bring it down to Earth. I think that idea has been contemplated in a way. There was a mission a while back that aimed at capturing an asteroid and studying it up close, and I think that's along the lines of the question that was asked.
Yeah. Do you have anything to add, Gerald?
Yeah. Back about 10 years ago, there was a proposal for what was called the Asteroid Redirect Mission, which was an attempt or a suggested mission to go out and actually capture a small asteroid, bring it closer to the Earth, and put it in orbit near the moon. And it wouldn't be brought down to Earth. You don't want to do that, but putting it in orbit near the moon so they could study it. That mission eventually kind of fell by the wayside. Then it became a mission to go grab a boulder off of an asteroid and bring it closer to the Earth. But that's pretty much also gone by the wayside as well. So I don't think there's any current plans to go out and grab an asteroid and bring it near the Earth.
But theoretically speaking, could we do it?
Theoretically, yes.
Well, theoretically, it happens all the time in that naturally you have bits of rock falling through the atmosphere and landing on the Earth. When they're in space, they're asteroids. As they go through the atmosphere, they're meteors. And when they land on the surface of the Earth, they're meteorites. So you could certainly nudge an object into an orbit that will cross Earth's and have it fall through the atmosphere. And there's another point. We've brought back, we're bringing back samples from 2 asteroid missions. It's really exciting. There's a Japanese mission and there's an American mission. And so we're bringing back already bits and pieces of them for the purpose of understanding them from the science perspective. There's already been a sample return by Hayabusa, which was a Japanese mission to the asteroid Itokawa. So have we brought asteroid materials back and landed them gently on the surface of the Earth versus having them whiz through the atmosphere as a meteor? The answer is yes.
Very cool. All right, so moving on. Someone else is wondering how big the average asteroid is.
Well, quite a range. They can be as small as 1 or 2 meters, and they can be as large. I think the largest near-Earth asteroid is 26 kilometers, and then of course you've got the asteroids out in the main asteroid belt, which are even larger. Tom talked about a couple of them earlier.
Well, how do you define an asteroid? At what point does a bit of material in space become an asteroid? And that would kind of help you along. Certainly Gerald understands this very well, and that is at some point in time, the object is going to become so small that you'll never detect it, so you can't see it, and you can't form an average, so you wouldn't know. and the collisional process kind of produces a power law in sizes. And when you get to very, very small sizes, this power law rolls off. And that may be just because there's a selection bias. We just can't see what's out there. The pieces you want to look at are too small.
Right, right. Yeah, there's a lot of debate about the term meteoroid, which is sometimes used to refer to asteroids that are 1 meter or less. But there's not a lot of agreement on whether that's a valid definition or not. So as Tom says, at what point do you just say it's a rock out in space versus an asteroid?
Awesome. Thank you. That was really interesting. Another question we got from Kathleen was why asteroids are mainly between Mars and Jupiter.
Oh, okay. Do you want me to take this one?
Yeah,
Gerald?
go ahead, Tom.
Yeah, and I kind of touched on that in my talk. So you have to imagine in the early solar system, you had the sun and a protoplanetary disk, and the density of that disk probably decreased as you moved away from the sun, as you radiated outwards. And you had the inner planets forming, and you had these embryos growing close to the sun and going outwards. All kinds of interesting processes that would have occurred. But one of them was the early formation of Jupiter. So Jupiter grew very large, very fast, and its gravitational forcing, nudged objects out of the region between Mars and Jupiter, and in fact impacted the ultimate size of Mars. Okay. And so you had processes of planetary formation happening in that gap between Mars and Jupiter. And as Jupiter got bigger and bigger, you ended up scattering those materials out and removing them. And so you ended up with a mass depleted region. And so now the question is, why so many? Well, there were also collisional processes during this time, and you were breaking objects apart. So rather than having a growth process where you were forming larger bodies, whatever was left there, and in fact, would be the broken up pieces of the embryos that had started to form.
One of the interesting things is that if you add up the total mass of all those asteroids out in the main asteroid belt, it's actually less mass than our moon. So as Tom said, a lot of the material was actually scattered out of the solar system or thrown back in towards the inner planets. And although there are millions of asteroids out in the main asteroid belt, the total mass is not actually all that great anymore.
Awesome. And our next question was, how do you tell the difference between an asteroid and an Earth rock? Like if you found a piece on it.
Okay, I can help with that. So this is a meteorite. So an asteroid, when it's on the surface of Earth, is a meteorite, not an asteroid. Asteroids are in space. So that's a cool question. And so there's several possible indicators to tell the difference between a rock that fell from space, which is called a meteorite, and an Earth rock, which we sometimes call meteor wrongs. Okay, and this is a meteorite I'm holding. And this meteorite is actually an iron meteorite. And so in my hand, I'm holding what used to be the inside of a planetary core, a small body that completely melted and formed this iron blob of metal, very much like the Psyche mission, the asteroid Psyche that we talked about. In fact, this particular meteorite's a good analog for that. But I don't know if you can see with the light and everything, but you see the little divots. Let me see if I can do this, but there are little divots in this rock, this piece of iron metal, and those were formed as a meteorite passed through the atmosphere. And so, as you go through the atmosphere, you have friction, and you form what we call regmaglyphs. These are basically little fingerprints on the rock. I can spin it around a little bit more so you can see them. So if you see a rock that's dense, because most meteorites, many meteorites, in fact, have iron in them, even if they aren't iron meteorites, then you'll have these features on the surface, these little divots that you can see. The other thing that might be hard to see, maybe I can do this one. Here's another meteorite. This is an ordinary chondrite, and it's really hard to see though. It turns out that as you pass through the atmosphere, you melt the outside materials and you form what's called a fusion crust. And so the rock might have a crust on it. But a lot of rocks have kind of crusty looking outer features. You can have desert varnish, for example. So because many meteorites have iron in them, you could try a magnet test and see whether or not the meteorite is, or the rock rather, is magnetic, and that might help you decide. Beyond that, you might need to take the rock to a laboratory and do more detailed analyses. That's my quick answer to your very excellent question.
Thank you. We have another just general asteroid question. And so someone was wondering how much an asteroid weighs, or probably would be more applicable is like, what is the average mass of an asteroid?
Well, it depends on the size and the composition of the asteroid. As we were talking about a few minutes ago, they can range anywhere from 1 meter to several hundred kilometers. And their composition can vary. The meteorite that Tom just showed you is an iron meteorite. A lot of meteorites have iron in them. Iron, of course, is very dense, and so a meteorite or an asteroid that's got a lot of iron in it is going to be very heavy. But a lot of asteroids are made of more like silicate type rocks, like you would find on, in the mountains here on Earth. And there's an additional thing. Asteroids are not always solid rock. There's a type of asteroid we call a rubble pile asteroid, which is, if you imagine a gravel pile that you took out into space, and the only thing that was holding it together was just the mutual, very weak gravitation and some electrical forces that are holding it together, so that it's not very dense. It's going to be much lighter in weight than the same size asteroid that's made out of solid iron. So there's just a huge range of potential weights or masses for asteroids.
Thank you.
All right, we have a lot of questions, many that we probably can't get to this evening. But we want to thank each of you for coming, spending your evenings with us. And I hope you all learned something about asteroids. And we will hopefully do this again, same time next year for Asteroid Day. Thank you, Tom. Thank you, Gerald. Thank you, Ed and Helena and Banu for joining us. And if you missed any of the presentation tonight, it will be available on YouTube or Facebook for replay. And we are so excited to announce that we are starting live events, Summer Science Days. So check it out on the website starting in July, so coming soon. You can finally come back to the Science Center for just a few brief events. Thank you again for joining us. Thank you for your donations. It's never too late to contribute. And we will see you at the next event.